Oh, cool. All right. So another way to kind of develop a possible form for what the slope looks like for calculus, for something that's not a straight line, is it's basically the same mathematically, but it kind of gives us another way to do this. Let's say I want the slope of f of x, but I wanted the slope at some point a. So then I can pick some other point near it. So in this case, this formulation isn't defining the distance away in h. Right? Remember, that's how far apart those points were. They're h apart on the x-axis. This is more just saying, let's pick a point near a and let it get really close to a. So slope here will be f of x. So now I've got the slope of f of x at a can be approximated by what's called the slope of the secant line. That's very interesting, huh? Secant line. So a secant line for us is going to be the line that goes through 2 points laying on the curve. So if I have actually got 2 points and I find the slope between those 2 points, that's the slope of the secant line. If I let the 2 points get infinitely close together, not right on top of each other, but as close to that as you could possibly be, that's what we're going to call a tangent line. And then later in the semester, we're actually going to make the connection between why it's a tangent line and does it have anything to do with the tangent in trigonometry. We will discuss that later this semester. We'll see the connection. So a secant line is when you calculate a slope between 2 definite points that lie on a curve. Are you guys with me on that? I like it. The closer those 2 points are to each other, the better the approximation the secant line makes for the slope at that point. Does that make sense? That's the same idea as letting h go to 0. I like it. So mathematically, they're both the same thing. It just kind of changes a bit the work we do to work with them. So this slope of the secant line is going to be f of x minus f of a divided by x minus a. Very similar to the other one. Certainly looks a bit different though. They still both use this idea to start with. So let's try an actual problem out. All right, so let's make a nice, easy function to work with. The answer, we can kind of make sense of what it means. That'll be kind of nice. Let's use a parabola, the basic parabola, f of x equals x squared. Kind of word it close to the way you're going to see it worded in the book. So fundamentally, do you guys kind of see what's going on here? This is a marriage between those 2 different ways of looking at the limit. So I've got a secant line between 2, 4, and when x is 2.5, you got to figure out what y is, obviously, so forth. But what am I doing to, what's the point of this exercise look like it's trying to get at? What the slope at what point? At x equals 2. Because I got the point that I'm really interested in, and I'm making a secant line, and those secant lines are approaching that point. So I can calculate the slope specifically for every instance. That's algebra. The crow flies line through those points. But I'm letting the points I use each time get closer to the actual only point I'm interested in. All right, so let's try the first step here. The math here isn't hard, it's just different than what we're used to. So let's see how this works. We're going to use this idea down here. So everybody got this here? Okay. So for part 1, I've got f of x minus f of a. So I've got f of 2.5. So this is my a and my f of a. That's the point I'm curious about the slope at that point. Every other point is just some specific x I pick. I got to revert back to you. You're the only one working well. So f of 2.5 minus f of 2. F of x minus f of a over 2.5 minus 2. So this will be 2.5 squared minus 4, right? All over 0.5. 2.5 squared. 6.25. I like it. So that'll be 2.25 divided by 0.5, which is 40. Well, let's see. 4.5. Thank you. I'm moving the decimal back. So that by itself, so visually, what we just did, this is kind of an interesting scale, that's all right. So we want to get the slope right at this point, but I went a little bit further, and so I got the slope, the secant slope, let me see, so this will be 2.5, 1, 2, 3, 4, 5, 6, 6.25, so it's about right there. So I got the slope between those 2 points, which in this case is a good approximation because the parabola really grows very quickly, and it almost looks straight when it gets out here. How are we doing so far? In fact, any continuous function, any well-behaved function, when you zoom in on it, it's going to look flat, just like the surface of the Earth. We're pretty zoomed in on it. Looks pretty freaking flat to me. There are people who believe it actually is flat. They still exist. If any of you are that person, I'm not sure what to do there. So that's what I got. This is a decent first approximation to the slope at that point, but it isn't. And then we step a little closer. Now the reason we do several is because if I can step, I can see a pattern, I can see what it's approaching. I can see if they seem to be approaching something. That's not a proof, but it's a decent feel for what it looks like it is. So what do I mean by that? I mean, I'm going to step a little closer now, 2.1. So I get 2.1 squared minus 4 divided by 0.1. All right, 2.1 squared is... 4.41. Thank you for saving me. 4.41 minus 4 over 0.1, which will be 4.1.
Upon 0.1.
I'm sorry, divided by 0.1, yeah. You guys, everybody with me? You guys do the last one. Do the third one there. Do the third one, the 2.01. Same way I just did those. This is going to be what section 2.1 looks like for the most part. These kind of problems right here. The math is not difficult, it's just a little different than what we're used to. What do you get for the top here? Or what do you get for this whole thing? Anybody got that?
4.01.
4.01? So if you had to hazard a guess, I want to see if you guys get this by now. If I kept going closer and closer to 2, the output would probably get closer and closer to 4. I like it. Now, on several levels, this makes sense. It's pretty steep here, right? It's pretty decently steep. If I just kind of drew in an estimation, I can actually get the slope of that line. I probably want to do it on a graph paper, just be more careful. And I should get something around 4. I should get a slope around 4. Because the slope there is 4. We just don't know how to get that better yet. This is not a proof. The slope there could be 3.999999997. I don't know, but this is a decent, I feel for it looks like it wants to be 4. Right? And how do I, now what's wrong with what I've done so far? Let me see if you guys are cool with what I'm talking about. I came in closer to that point this way. So obviously, I should probably also get closer to that point this way, right? So what I just did, let me show you the symbols for what we just kind of got a feel for. When we say it looks like it's going to 4, what do we mean it's going to 4? The limit, oh shit. The limit as x goes to 2 of f of x minus 4 divided by x minus 2. Is that, let me just make sure. What was a in this case? 2. And what was f of a? 4. So the limit as x goes to 2 of this, and actually be a little more specific here, because what's the thing? X squared. Looks to be 4. And now here we have a way we can actually check this. Does anybody see what we can do here? It's related to that very first problem we did. What can I do to this? Remember what I said about that very first problem on that warm-up sheet? We removed the problem. So what can I do here? What does that look like it wants to have happen? What happens? Because if I try to plug a 2 in here, I get 0 over 0, of course. That's the whole idea of I've only got 1 point. If I let x go to 2, I've only got 1 point. How could the slope possibly be done? That's what 0 over 0, that's one thing that means. If I've only got 1 point, you need 2 to get a slope. What the hell are you doing? But if I use the limit, why am I allowed to kill those? The limit doesn't get to 2. The limit doesn't get there. It just gets really, really close, which is what this is doing. So everything we do in section 2.1 about slowly getting closer to a certain input is doing the limit in a very, very detailed way, right? We actually do take a little step. Let's take a little tiny step. Let's take an even tinier step. Let's get really, really close to this thing, right? So that's the idea between now. Now this is beautiful. Because now if I let x be 2, what do I get?
4.
I get freaking 4, which is what our guess was. Of course I do. Right? So I could do the whole thing again. I could do it for 1.5, 1.9, 1.99, get really close to 2 from the other direction. So to be really honest, what we have just done is something like this. You ready? We didn't go to 2, we went to 2 from above. The little plus symbol means from above. Then we can do the whole thing again and go from below. And if those two agree, that's a proof that it is that number. All right, trying to lay some groundwork for stuff we're going to be doing, well, I say later, but later today. Okay, maybe. How do you guys feel about that? The math involved in this is easy. It is just slopes. But there's a bigger idea. It's slope, 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 and they're all trying to show you some bigger idea. Trying to approach something.
If they're estimations and not exact values, shouldn't we use the estimation symbol?
No, these are exactly equal.
Okay.
And I said this looks like it's going to 4. Right?
Yeah.
So this was proven. But if I didn't do this step, yeah, I could say approximately 4, sure. Because this is, it could, like I said, it could be 3.9977. You know. This is not a proof, but this one is a proof. I simplify this, I plug it in, I got the number, it's 4. That's what it is. I love it. Okay, I like it, I like it. All right, the next kind of level to this. So this, you gotta let this be nice, because you can sink your teeth into this. It's just a bunch of plug and chug. It's beautiful. Then you gotta step back and look at all your work and see what it's kind of going towards. Okay, that's that extra little layer on top. The next level of this is nowhere near as detailed, but it's got the important concept of a limit. So let's see if I had. Let's do this. Yeah. Okay, I like it. Doesn't matter what that is. I love you guys. You're like, I ain't drawing that shit. So, I'm just going to watch and then look at the video. Okay, now, let me just ask you this question. See what you guys think. This is a graph of some function f of x. What is the limit as x goes to -2 of f of x? Could be. Okay, good. Your gut's right. The limit is 1. Why does it not matter? What is, so that limit is 1. What is f of -2? What is f of -2? Undefined. Beautiful. The limit does not give a shit what is actually happening there. It's just, what does it look like it's doing? Where does it look like it's going? So if there was a big, like, sinkhole in the middle of the road, and I was following along, you shared your location with me through Google, and I could watch your little blue dot moving around. I see you're approaching this sinkhole. Do you actually ever get there? Hopefully not. You're like, don't get any closer. You understand what I'm saying? So you get really, really close. You're approaching the sinkhole, but you don't get there. So there could be like a temperature at the sinkhole. You can keep recording the temperature as you go forward. You're like, oh, we got to stop now because we're going to fall in. Oh, shit. So I always talk about, also, there's a movie called, there was a remake in the 80s, a movie called The Blob. Very good movie. At the very beginning, if the guy would have just incorporated a limit into his life, the movie wouldn't have happened. Thing falls, little monster comes crawling out, little blobby thing. This guy comes up and gets really, and touches it. I'm like, why? What? Are you kidding me? If he would have just gotten really close and not touched the damn thing, maybe it wouldn't have eaten him and gotten really big and eaten a lot of people and stuff. So the limit is you just never get there because something weird might be happening there. Is something weird happening at -2? Yes, there's a sinkhole there and you don't want to go there, right? Now why is the limit, now watch this. Is that cool? All right. So that's one thing. What's the limit as x goes to 0?
-1.
Is there only one way to drive towards that value?
3.
If you drive towards it from this side, it looks like the limit is -1. I love the fact, is everybody cool with, I love this. Hopefully this is true. Normally students have a lot of trouble about adjusting the way they look at a graph. They're like, well, no. As your x's get close to 0, what are your y's doing? If I'm going from above, if I said that, now you could tell me what. So if I drove towards the sinkhole from above, meaning my x's are above 0, my little car is going towards what output? -1. What if I did it from below? You can see why that above and below is weird, because people think this is above, this is below, but this is x. From above that x value, from below that x value, my little car is going towards 3. So if I try to say what's the limit as x goes to 0, period, since you guys didn't agree on what it does, it's what somebody said their correct phrase, does not exist. There can't be a limit because there's two different possibilities. So the limit does not exist. There's two limits, depending on which way you're going. So the limit as x goes to 0, period, of f of x, does not exist. They have to agree for the limit to exist. It wouldn't make sense to say the limit when there's two possible freaking limits. Does that make sense? You gotta love this shit so far, right? Hopefully. Not too bad. Maybe very new to a lot of us, but not totally difficult. Yes?
What's the difference between the circles again?
Open circle, of course, means
A whole asymptote.
not included. Whole asymptote, I love that. Who said that? Whole asymptote? No, not included. And a closed circle means included, right? It's just like shading on a number line. Unshaded, you don't include it. Shaded, you include it. Is that cool? Okay. And that's why f of -2 is undefined. There's no output for -2. Just a break here. I like it. All right. So it seems that in order for, so if the limit as x goes to a from above equals the limit as x goes to a from below is some limit, is some number L, then I can say the limit as x goes to a, period, is L. Otherwise, the limit does not exist. So you can have about left-sided limits, right-sided limits. They could each have an answer, but then the limit itself could just be does not exist because they don't agree. Now, what if I did this, added something to my little picture here? What's the limit as x goes to -4? Now, officially, it does not exist, but we can say more specifically how it does not exist. It goes to negative infinity, which is another way of saying don't exist, does not exist, but it's a more specific way. So it's equal to negative infinity. Does it ever get to negative infinity? Well, you can't. If you ever find something that does, let me know. If you get to infinity, I think you obtain the next level of consciousness or something. If that, I guess you can't let me know. So send me an EM signal or something, let me know. Is that cool? You can have those negative or positive infinity answers. They are types of does not exist. So if I said, the sky's the limit, that's another way of saying there is no limit, which means it's infinite, right? I can do infinite so forth stuff. All right, so I think you're ready. I want you to try this.